अभी समय है, अभी तो 7:30 अभी हुआ नहीं है.
ये हिमांशु जी,
सर
एक क्योंकि मैं मोबाइल से ये कर रहा हूँ,
ज्वाइन कर रहे हैं.
तो अगर कोई ये पावर पॉइंट प्रेजेंटेशन अगर देना है तो पॉसिबल है क्या?
पॉसिबल था, वन शेयर का था
क्या?
मोबाइल में आप जब जाइएगा तो वो शेयर करके आता है.
अच्छा,
शेयर से आप शेयर कर सकते हैं. आपको
लेकिन उसके लिए फिर ये चाहिए ना पावर पॉइंट सॉफ्टवेयर.
हाँ
हाँ, मोबाइल में
चाहिए. यस यस, माइक्रोसॉफ्ट विंडोज का कुछ चाहिए.
वो उसमें होगा आपका.
नहीं तो आप पीडीएफ
PDF,
बना के
हाँ.
मोबाइल पे ले सकते हैं.
Correct.
ओके.
Best thing is to make a PDF and show the PDF. बस.
हम्म.
सही कर रहा है.
अच्छा,
उससे क्या होता है कि all these vagaries and uncertainties of Microsoft doesn't come in.
Right.
Just show the PDF.
So
Yeah.
So it's the time 5:30. Are you ready, sir?
Yeah, I'm ready. Yeah.
So on behalf of IEPT RC19, we have all the
कैन
participants.
आई हैव 5 more minutes? पीडीएफ बना के ट्रांसफर कर लेते हैं.
Okay. So you will join later.
जस्ट
हम लोग
5-10 मिनट में.
अच्छा, तो हम लोग शुरू करें.
या
Okay. So I now request that today's resource person, Utpal Roy sir from IIT Patna to start the session.
वो क्या आज एक टॉक है कि क्या है आज?
The two talks,
Then followed by.
followed by AN sir, Amrin Nayan.
ठीक है, very good. Excellent.
Okay. So thank you, Himanshu ji, and so let me start my second talk. I'll share my slide.
I will be going also on my mobile, huh? So
Yeah.
so for a few minutes I may not be on. That's it.
Sure. Yeah. So,
Because हमारे यहाँ कुछ चल रहा है काम.
हाँ.
So some work is going on in our society. Okay, please
Is
start.
the
I'm
slide
sorry.
visible?
Yeah.
No, it is visible. Yeah.
So fine. Now today, I'm supposed to present on quantum technology as a whole. However, I'll be emphasizing on quantum computing and sensing. I'll try to give some examples as well as some basics. Though time is very limited, I'll try to kind of wind up things within time. So, as a whole, quantum technology has many integral components, and here it is Q for quantum, and this is quantum communication, quantum computing. Uh, I'll stop my video because I don't know why. Yeah, just give me a second. Yeah, can I stop sharing and share again? Because
Sure.
yeah, just stop my video with
I can stop.
slide is a bit slower, so that's the problem. Yeah. Yeah, so fine. Yeah, so quantum communication, quantum computing, quantum sensing, quantum security, and quantum machine learning. And there are several more, sub areas where quantum technology is connecting and making an integral field, which is quantum technology rather. So here I'll be, talking about several points, but we have to understand that how things can move on. Uh, First of all, few words which are, may not be familiar to students in the beginning, but I'll come one by one. So there are two things which are on top, quantum entanglement and quantum superposition. So these are the most important ingredients of quantum technology. And any of these essence, in addition to additional things of the quantum systems will comprise of different useful models with physical parameters. And then one has to look for a stable information which can be measured, and simultaneously experimental design and measurements has to be done. And then finally, that measurement is not enough. That is the starting of the technology. And then one has to think of fruitful measurements which can connect to the industry and society, and then make a device which is useful. So this all this process has to be like continuous to have a fruitful quantum technology in society. And here, always people look for physical system. Physical system means that to implement any technology, we have to think of that where and by what we can apply. For example, laser. When we talk about laser, laser was prepared in a medium and then it was used. So that is the kind of thing one has to think of, even if either it is classical or quantum. But this is some physical systems. There are more systems which are little difficult to understand and not in the textbooks. For example, circuit, quantum electrodynamics, and NMR, and little more things. But here I'll be talking about light, atom, and molecule. So which student normally, you know, hear about these things in the textbooks, that light, atom, and molecule. And here at IIT Patna and nearby places like in India, there are many groups working on these aspects, quantum optics, various aspects. I will not get into those things because time is limited. Now, as I said that there are two components. These two components like quantum entanglement and quantum information. So these two are the salient different aspects which have no analogy to classical system. And this is completely different from classical system, and that makes the quantum system so robust and useful. So quantum entanglement and quantum superposition. So if we go for the efficiency of quantum uh, computations and quantum effects. So long back, Gordon Moore has predicted that this transistor, the 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 the, the transistor number of transistor per unit volume is going exponentially high, and that should go on like this. But however, people have beyond 2020, 20 and before that, people have are observing a saturation of this curve. So it's a practical curve where you can see many known processor over here. Many places you see Pentium 4, which comes around 2002 around, and then you have I series, Intel I series. Now we have probably the recent one is i9, and you have 13th generation or so. So this is how things are developing. However, if you see the curve, it goes up, and then somewhere now it is going to be saturated. So now in computer companies, either it is desktop or laptop, what are they doing is they are having a processor which is not much faster than the previous processor. So what are they doing? They are optimizing the things, they're minimizing the loss, and they are having multiple cores to make it more efficient. So that is what they are doing. But if we just talk about the efficiency of a chip, that cannot go off indefinitely. The reason is very simple, that always we know the initial bit of information, classical bit of information, which is represented by on and off. Initially it was quite big, over a table or so, and but with time that has gone down like anything, and then we have a lot of sophisticated chip in ICs inbuilt in the circuit of laptop, and and the size of the transistor, size of the chip goes in the level of molecule and atom. If it goes in that scale, then your classical theory by which you have been explaining is no more applicable. And there your quantum theory starts affecting. However, now it is unfortunate that as soon as your quantum theory starts, you need to use that quantum theory, then your previous knowledge of transistor and other things will not work. So you have to, start over again from zero. So that is what is happening, that people have been, trying to have physical systems where they are defining bit in quantum system, and then things are going on in a similar way. But this is unavoidable because you cannot improve the efficiency of the processor anymore, and you have to go into the quantum domain. So here it is some difference of quantum computing. These are some remarkable steps. There are many intermediate steps, but Richard Feynman and then David Deutsch and Source, Peter Source, they are the person behind uh, quantum Turing machines, then quantum computations, and the factorization, some algorithms development. But if you look at right hand side, that this is a difference between quantum computing and classical computing, major differences. The first row, if you can read it, is fine. Otherwise, I'll just mention. First row says that that quantum computing, in classical computing you have on and off. So if on is 1, off is 0. However, in quantum computing, you have many intermediate steps. In classical computing, if you switch on some light, then if it is either it is on or off. But in quantum, if it is quantum system and if you define 0, 1, there are many intermediate states. Then in classical computer, the power increases in this way, is linearly going up. However, the power increases in quantum computer is exponentially high. So that's another advantage of quantum computer. In classical computer, some advantages you have, that low error rates, and it can operate at room temperature. And however, quantum systems are very fragile. You have to work on very low temperature. So these are the best difference. In classical computing, you can actually handle with actual computations of classical computer. But then, however, in quantum computer, so far it is based on simulations and running the kind of data in virtual computer. So this is the status of both the computers at present, and yeah. And let us now things which are required. So this is called quantum superposition, which I just mentioned, and I'll be again mentioning that. So quantum superposition is number one. Then then this thing is that the quantum computer can actually store a lot of informations, and it can also be very fast. So in classical computer, if something takes few minutes, then in quantum computer, it can be indefinitely faster. Okay. And the third thing, that quantum particles, which are very tiny, can behave like a wave. So it is not the way it is drawn, but this is just a very basic cartoon. But quantum particles can behave like a wave, and that adds up to many properties which are helpful for quantum technology. And then the concept of qubit. So when you have bit in classical computer, this is the bit which is classical computer, and quantum we say quantum bit, and then in short we call it as a qubit. Okay, so in classical it is bits, in quantum it is qubit. So qubit in quantum system is defined as 0 and 1, these two things, and also it can have combinations of 0 and 1, lot of infinite number of combinations of 0 and 1. So that's the idea. And then the fifth one is entanglement, quantum entanglement, where you cannot separate out states. I'll come to this point immediately after this slide. So this is what quantum entanglement is. The students who were there in my first talk, I mentioned this thing, that this is a very important slide to understand quantum entanglement with the classical correlation. Say, for example, that I have this chamber where two balls, one dark color, one is white color. Now I have kept these two balls over here, and then this machine is actually shooting the ball in both the sides, and this person is having receiving the ball which is white color. Now what will be the color of the other with the other friend will be definitely black. What is the reason? The reason is that you knew previously that you have kept both the balls, one is dark color and another is white color. So that is why it is known. So it is called the hidden variables, that there is some hidden information which is associated with the system prior to experiment. So when you did the experiments, before that you knew the information that there are two balls of different color. But imagine that you do not know this information, that what are the colors of the ball, but you just keep it, close your eyes and then keep two balls, and you do not know the colors. And then if you receive white color, you are never sure that your friend will receive the black color. So he may receive a white color as well as dark color. So both the combinations are possible. So in that case, we do not have any hidden variables. So this is the difference from a classical situation of hidden variables or quantum situation of hidden variables and quantum mechanics where there is no hidden variables. So if you do not have a hidden variable, but you have some correlations between these two, then they're quantum mechanically entangled. So this is the biggest difference of classical and quantum correlation. Okay. So this is how two persons are named as Alice and Bob, and they shared some common state, which is, I said that inside the box the balls are kept. So which is analogous to having the interaction, the both the states are interacting, and then you can actually send the information from one place to another. So using the power of entanglement. So here if you see the state, the shy red color state is with Alice, and the blue, which is phi state, is with Bob. Now if you have a state psi phi plus phi psi, so these are not the product of the state of Alice multiplied by the state of Bob. On the other hand, it is the superposition of Alice state multiplied by Bob state plus Bob state multiplied by Alice state. And this is the reason that they are not in the form of factors, and you cannot separate out their states indefinitely. So any measurement, if both of them carry the state, then at any distance, if Alice measures the state, the Bob will definitely get the other one. So without, Alice will come to know if Alice measures one of them, and then Bob will give the other one. So for this, they don't have to talk to each other. They don't have to come like near to each other, and they don't have to do anything. Only requirement is they have to share a state, quantum state, which is a quantum entangle. So this is very interesting and quite, surprising phenomenon of quantum mechanics, that quantum entangled states can be measured and the information can be known from any distance. So this has a strong, applications to quantum teleportations. As I said, that information can be sent from one place to another place. So this is called like teleporting quantum information from one place to another. So how it is done? So this is one example that I showed in my last talk, that this is a old data, but this was there in my slide, so I'm showing it. But one can actually look for the recent one, which is over 2000 kilometers phase-based satellite communication. So basically, in between two big countries can be done, quantum communication can be done through
Oh, all
satellite.
right.
Okay. And these are also, some pictures of quantum computer. The first one is to solve quantum computer to solve some puzzle, Sudoku puzzle, many of you may know. And this is a Google quantum computer, but these are all improved nowadays. So one you can get very good pictures. Just give a quantum computer search in Google and go to images. You'll see that how sophisticated the computer look like in recent time. So this is also another one which NASA's artificial intelligence lab. So different kind of quantum computer I tried to give you, and definitely will get a lot of other recent pictures in internet. Now, what is the difference of, as I said, that quantum bit, which is qubit, can have infinite amount of information. So classical bit, you see here it is classical bit 0 and 1, and this is qubit, it is quantum bit. Now the 0 is the north pole and 1 is the south pole of a sphere. Imagine that this is the Earth and North Pole is defined by 0 state and South Pole is defined by 1 state. Now, how many points you can have on the surface of Earth? That is infinity, right? So, and each and every point can be one information in quantum system. So definitely, so infinite amount of information can be, kind of stored in one qubit. Whereas in classical bit, you have only 0, 1 informations. You do not have any combinations. So that is why it is another power of, quantum computer, because of superpositions of this kind, various kinds of superpositions, which I have actually shown here, that, cos theta by 2 0 plus some factor of 1. And because these factors are actually commensurate to have these points on the surface of the sphere, and then this combination will allow you to have infinite points on the surface of the sphere where the north pole is 0 and south pole is 1. So infinite points. So this sphere is called the Bloch sphere. Okay. Um, yeah. So yeah, here you can see the Bloch sphere operation. Um, and this is actually is shown for quantum gates. Now, once we define quantum bit, which is qubit, the next step is should be you have to design quantum gates. What are quantum gates? Like different operation you are doing. Now there are Pauli matrices which will give you Pauli X, Y, and Z matrices, where you can see that how they are operating on the Bloch sphere, and there are other gates like phase gate, T gate, Hadamard gate. All these operations, like here in the first place, this goes from 0 to 1. So, so now you see that how it goes from North Pole to South Pole. So this is how on the surface it goes. In the first case, it is Pauli X gate. Second case, it is 0 to 1 again, but you see that in the y direction, so it goes like this. And in the z gate, it goes on the equatorial plane. So from one point to the opposite plane, so it goes from plus to minus. So this is how the gate operations, these are the three Pauli operations, basic rotation operations based on which the single qubit gates can be manufactured. And this is another very important gate, which is Herambert, the fourth one. You see that it comes to the equatorial point from the North Pole. So it is from 0 to plus. Plus means 0 plus 1 by root 2. So this is one is the equatorial plane, and the other gates are operated this way. So a single qubit gate 101, any gate, logic gate, can be operated on the surface of this particular sphere. So that is the importance of such kind of Bloch sphere in quantum computing. And on the bottom, I have written that quantum bit is A0 plus beta 1, where AB can be any number, but it has to be like A square plus B square should be 1. So normalized. Otherwise, this can have infinite combinations. Whereas the classical bit is 0 or 1. It is not both 0 and 1. It is 0 or 1. Now let us see that once I know 0, 1, and also I know how to think of logic gate, then it is basically worthy to have some. Am I audible? Yeah, can somebody tell me whether I am audible? I am online now.
Now you're audible. Yeah. For a while
Yeah,
you
yeah,
were
because
unaudible.
there's some power cut here, sudden this thing. So yeah, so I'll continue from here. Yeah, so now I was talking about this after this qubit and the logic gate. This is the quantum circuit. So because we have to have quantum computing, we have to have quantum circuit. So this is a simple quantum circuit to have entangled state. So you have Hadamard gate, which I have shown in my last slide, and this is a control node operations. This is the first place where I am mentioning that a 2 qubit operation can be done. So Q0 is 1 qubit, then this is called that control not operation. So when the q0 will take a value 1, this will actually flip. So this is how the c naught control not operation takes place. So if you have a combination of these two gate, one logic gate is Hadamard gate, which is shown in the last slide, and this is a control not gate, and then you will get a state which is of this phi. You cannot factorize a state, and then we call this as entangled state. So a simple quantum circuit can entangle two quantum bits. So that is how you can use quantum computing circuit in the simplest case. And now it is also possible in today's time that in freely you can have IBM Qiskit simulator, and then you put the same circuit over there. It will give you the probability. You see that almost half and half. So that this is actually 1 upon root 2. So the probability is half. If you 1 upon root 2, that will give you half. So ideally you should get half, but then because it is realistic virtual computer, so the computer is there, but it is not in front of you. You give the circuit and then put it in the queue, and then they can perform the simulation on the real computer, real quantum computer. So this is how it is. Okay. And more examples. So this is the state of this kind. As I mentioned that Alice and Bob are sharing their states, and then they are quantum mechanically entangled. Now, how we can have quantum teleportation with quantum circuit? Just for you may not understand the whole protocol, but just to have an idea that how quantum circuit works. Now you see that the Alice has to have some qubit, Bob has to have some qubit, and then this is a classical connector. You may not think about this thing. This is for measurements. So Alice has 2 qubits. Yeah.
We couldn't hear you. Imanshu.
Am I
Now
audible?
you are, but in the middle
Yeah,
you were not
so
audible.
yeah, there was a lot of problem in power cut. Now I have connected to my mobile. So let me manage this way because otherwise frequently. Slide is- Yeah, am I online or audible to
Yes,
all?
sir. Yes, yes.
Ah, okay, okay. So a lot of disturbance today. Okay, so let me continue. Yeah, so I will just start with the previous slide that I was telling about that different quantum circuits in the quantum entanglement and teleportations, and then I was moving to another aspect, which is machine learning, which is also a very important field, uh, just like quantum computation. So they go hand by hand, because uh, you also need a quantum computer which is efficient, can perform a task, and in recent time machine learning is also quite hugely evolving, and this has applications in almost all areas. So in future this will be one combinations which will be unique combinations. So in algorithm part in machine learning you can actually have lot of robust algorithm using quantum states, and there you can apply quantum entanglement and quantum uh, superpositions for building up this kind of entanglement, and that will be useful for interesting tasks. So let us just give a one example of the task which quantum computer can perform if you apply that kind of algorithm. So you may not get into this algorithm, but just see the example. So this is one original image, and you can see that A, B, C, D, E up to J, they are actually having noises. Like when you take photos from a mobile, different mobile has different quality of pictures, and imagine that we have such 10 different pictures A to J, where the original was T, and none of this. So this is a real figure which you are taking the photograph, and then there are 10 combinations with noises. So how do I know that which noises are greater? This is just some layman example for quantum computation for this algorithm. So algorithm, the circuit which I have given in the previous slide, can actually perform a task where you can have image, you can differentiate these images, and you can have a ranking of the images starting from, you see the similarity which is 1, which one is nearer. So this is the nearest, where you have 1, and then you can have this dissimilarity, like if it goes away from 1, then they are actually not similar. So 0.97 is closer to 1 compared to 0.95, and then so on. So this is how the ranking goes on, and the first one is A and last one is J, and you can also see the noises are going high. And who performs this kind of task? Oh, this is intuitively very obvious, but this is performed by quantum computer and the circuit which is given in the last slide. And this is another kind of task which is a classification task, where you can have the nearest neighbor. You can see the circuit over here. So this is a new algorithm, and you can have a circuit. You can have different data, A, B, C, D, and then A, B, different kind of data. So this is one branch of data. This is another branch of data. And this classification, you can see the boundaries, just like the boundary of the countries in the world map. You can see the boundaries which is actually separating a different kind of data, and this performance is actually carried out by the quantum circuit which is given here. So quantum computer has many aspects of such thing, and and lot of aspects. It's not only computing arithmetics and solving problems, and but also a lot of other things which is connecting to the society. So these are the some percentage of accuracy and a lot of other parameters. So this is all about quantum computer. Like we have to start with the bit and then qubit, and then bit and qubit there connects to quantum entanglement and quantum superpositions, which can perform tasks like quantum teleportation, sending information from one place to another, and then image processing, completely different example. Then a classification task, for example, that image processing, for example, you have MRI images and you don't know that which patient is having a particular disease, and you have multiple images, and then you can classify, and you can say, okay, this is the image, MRI image, for which this disease is existing. So that kind of task normally machine learning does, and also quantum computer is capable of doing that, uh, as I saw. So now let me get into quickly to quantum sensing. Now, when I say sensing, so this is actually the work performed by a sensor. Now, what a sensor does, sensor measures some particular physical parameter very precisely. For example, if I want to measure a length, then I measure by a scale, a meter scale, and then I can probably have measurements with the error in the level of say millimeter. Then if I have a a slight calipers, then the error is much lower. And then if you have sophisticated measurement devices, your error will go down. So similarly, so how precisely you can measure something, that is the part and the field called quantum metrology. And the device which can do that is called the sensor. Now, can I have some sensor in quantum system? That is the point. So this is the part which I am going on, that a sensor from quantum system. So what will be the starting point of it is I wanted to start from your known point where the textbooks are explaining about the classical oscillator. Sometimes it is pendulum, sometimes it is spring, sometimes it is string. So different types of harmonic oscillations, and these harmonic oscillations are also having quantum version when you think about atom, electrons, wave packets, and different things. So let me give examples of a quantum world of harmonic oscillation. So here I have to mention about the Schrodinger. Schrodinger long back has mentioned about the wave packet of harmonic oscillator. So if I have a quantum wave packet, quantum harmonic oscillator, then this wave packet exactly follows the trajectory of oscillator, just like pendulum. So this is what he has observed in 1926, and later on it was verified many times to have um, the coherent state, something called very coherent state. The wave packet should be coherent, like you see in classical physics, water wave, light wave, everything is very coherent. So where the waves are superposing with a constant phase difference, and in quantum mechanics, if such thing happens, is called the coherent state. So a beautiful example is laser. When you see laser, they are very highly intense, a particular color, right? So this properties comes from the coherence of laser. And if the laser is described in quantum mechanical approach, then also it is nothing but a coherent state. So I would say that the coherent state, if you just think coherent state and laser, they are same. A quantum laser and a coherent state, they are analogous. Now, Roger Glover in 2005 got the Nobel Prize to have how you can characterize the coherence. It is just to mention that the quantum coherence, how the wave packet and the particles can interact each other, have correlations in between. That is actually elaborately studied by him, and also our ECG Sudarshan during the same time. Then R.J. Glover has got the Nobel Prize in 2005. Now, as I said, the wave packet, now you see a Gaussian wave packet, how it moves. So this is the wave packet of a molecule, just for demonstrating that how the particle in quantum mechanics should behave. So particle is not definite, and classical particle is just a dot. You can see the dust over the screen, dust over the computer screen or mobile screen. Those are classical particles. However, in quantum particles comes with the probability. So it has a distribution, you see that it has a Gaussian distribution, and it can also change with time. So in classical particle will be more or less as it is unless until it decays or evaporates. Uh, but quantum particles are supposed to change in most of the time. Yeah, so this is the coherent state. This is a Gaussian wave packet, and this is a coherent state, just like laser. As we have seen that, if you use a very cheap laser, which is a pointer we use on the screen, that's not very expensive. So it's a very cheap laser. You can use it, and then a wall far from your place will also have a point focus for the laser. So if it is a red laser, you will see a very small spot on the wall which is far away from you. So laser is that much coherent, and that you can see that it does not decay. Okay. So yeah, so that's the property of the laser. Even if it is quantum mechanics, but if you have a perfect coherence, just like laser, you can have a non-decaying wave packet. Okay. So then quantum superposition, which I started with in the beginning, I said that there are two properties, quantum superposition and entanglement. So here I use quantum superposition for quantum sensor. How we can do that? I have to start with story of Schrodinger cat, which I mentioned in my last talk, but I'll reiterate because some students probably was not there. Say this is a closed box, and then there is a cat inside the box, and then you have poison in this beaker, and there is a hammer over it, and this hammer, if it falls down, then the beaker will break, the poison will come out, and the cat will die. But how the this hammer will fall down, that there is a radioactive element in this box. If there is some radioactive element emitting which is spontaneous and random, we cannot have a control over it. If there is a radioactive element, then the hammer falls, and then beaker breaks, poison comes out, the cat dies. So from outside the box, you never know whether the radioactive element has come out and the cat is dead. So then, it is a confusion from Max Born and Schrodinger. There was a debate of this thing, the whether the cat can be in a superposition state of both live and dead, because it has a 50% probability to remain alive and 50% probability to remain dead when you open the box. So is it in a superposition state? The so this is not a quantum system, but this was the analogy given to Schrodinger to prove that the superposition principle is wrong. But then Max Born has defended his theory by saying that if you open the box, then you measure the state. When you measure it, it cannot be in a superposition. So quantum physics, when you measure, the state collapses. So you actually get one of the states, but it is in a superposition state. And if you go to quantum mechanical state now, similar analogy, you have one live cat, one dead cat. Now, because it is quantum mechanics, you also can have a quantum interference region in between where there is no cat. So this region is due to quantum interference. The live cat and dead cat, they are not coming to each other, and this interference is even if they are far apart, they can have some probabilities in between, and this is called quantum interference. So it has no classical analog. You know many classical superpositions, just like you see ripples in water, and then you see light interference. Such interferences are completely different from this interference. So this only happens in quantum system, and this can have a different orientations, different size. They can be nearer, they can be far, and so on. So depending on that, you can have a lot of varieties. This is first one is called Schrodinger cat, because live cat, dead cat, and superposition. This is called Schrodinger cat. Then you can have a compass like situations. Like compass means there are four of them: north, south, east, west, and then there are these dots. There can be multiple of them. Now, let me give examples of it. Some examples which in our lab we have been doing. So, matter waves, like the matter also can be wave. As I said in the beginning of quantum computing, that the atom can behave like wave, and so those waves are actually matter wave, and matter wave is dominant in low temperature. So the question is, because it is wave and quantum mechanics, can we also have some quantum informations over here and quantum sensing? Now you see that this white circle is a kind of a tunnel, white circle, just around the hip. There is a white circle, that's the tunnel, and there is a small peak over here, that is a quantum particle. There's a quantum matter which behaves like a wave. So it is a quantum particle, and then you have a tunnel. Now, my question is, if I just leave one particle like this on the tunnel, one point of the tunnel, what will happen after some time? Now, let us see that what will happen. So this is the situation from top. If I look at it from bird's eye view, that this is the tunnel, white patches. from top, and this is the particle from top. Okay, now let us see what happens. So there's some animation, but now that I'm using other internet that cannot run, so this will actually have this kind of snapshots, and after some time, some millisecond of time, which actually experimentally observed, you can see that the initial particle, because they're quantum, they are described by probabilities. The probabilities can split into two, probabilities can split into four, probabilities can split into five, six, probably here 12 of them. So these are the ways that the probabilities can split along the tunnel. So this is quantum information science with the matter wave. Okay, and this can be seen here. Now the interesting point is that if I switch off, I'm not getting into details, if I switch off the potential, this tunnel potential, is all these probabilities will come to the center and they will have interferences, and these interferences is very sensitive, is very sensitive. So you can actually measure precise measurements you can have at the center during the interference, and which will act as a quantum sensor. Okay, so this is just example that how you can actually make a quantum sensor in laboratory. Okay, second example, that atomic beam splitter. So if you read it again, it is atomic beam splitter. Now, in optics, a beam splitter is the element where one light comes in the input, and then you have two lights which is going out. So the beam is splitted into two parts. The most of the time they are 50-50. That is why they are balanced beam splitter or 50-50 beam splitter in optical laboratories. So can such thing happen with atom, which is quantum? The answer is yes. You can look at it here, that this spike, black spike, is the beam splitter, and this is the light uh, which is acted on by atom. So this is the atomic wave packet. This black spike is the beam splitter. Now what happens? It falls on the beam splitter. It splits into two. Okay, then they go far away, they comes back, I create two beam splitters, and you see the spikes here. These spikes, the sharp maxima and then this thing oscillations, they are actually the candidate for quantum sensor. You can have a very high precision measurements on these spikes, and you can see the structure. This is the in the phase space. I'll not get into that, but smaller the structure, smaller the area of the structure, greater is the sensitivity. Okay, and you can actually indirectly measure a lot of precision things. This is one example that you can measure picokelvin temperature, which is the highest precision so far achieved using this kind of system as atomic beam splitter. So quantum system use the quantum superpositions and make a quantum sensor of different kinds. So it's a indirect measurements of temperature you can do from quantum system. So this is another system where you can Harrows and Wineland got Nobel Prize in 12, but this is the setup by Harrows. Is the Sergei Harrows. And what happens that when the atom passes through the cavity, so this is the cavity, atom passes through it. So what cavity does? The cavity traps the light. You can trap light inside the resonator. So this is the resonator, and the atom goes and interact with the light. And this is what has happened. And now what happens that you have two cavities. One cavity is with this, one cavity here, another cavity here. I can create a state which is a superposition of both of them, and if you see in the middle, they are like checkerboard. Unlike a straight line, they are checkerboard, and each nodal points of the checkerboards will have very small structure. So by this, you can actually enhance the sensitivity quite a bit, and this is the power of entanglement. So in this setup, in the previous slide, we create entanglement, and then we can actually have very high precision measurements, which is a quantum sensor. So this is the kind of state we obtain, but out of entanglement, in the previous setup. So this is the state which you get, which is entanglement. And this is the quantum circuit we have used, okay, in this setup. And these are the structures. This is the real interference pattern which actually we have been pointing out. Okay, so this is the structure through which you can actually have a lot of measurements like gravimeter, magnetometers, precision sensing, and there are also other applications like inertial sensor, accelerometer, gyroscope. So there are also applications of atomic clocks and other things. Because now we have been using cesium clock, but then with time people have been looking for molecular clock. Sometimes it is lattice clocks and so on. So now this is a quantum scissor. You know the scissor, right? Is a kechi in Hindi. So you can actually cut things by scissor. So here I'll just mention that what do you mean by quantum scissor? So is there anything which we can cut? Cut means not the physical things. I can cut quantum state by quantum scissor. Okay, and that helps a lot in quantum information science and quantum sensing. So this is the kind of situation where you have these black circles are say coherent states. So this many coherent states, and if you have four of them like this, then you have superposition of this thing and also superposition of diagonal matters that I have already shown. So these kind of situations are called the compass state. But if you go for higher order, then actually you have these situations, and this situation can be engineered to have quantum scissor. So if you have quantum scissor, you see a very novel superposition states can be obtained. You may not think of what is S, N and other things, but a number of coherent states in a superpositions can give you cut the quantum state and say for example that I need a superposition of psi 1 plus psi 2, but the quantum state is having lot of other states. I do not need them. Now what I have to do, I have to cut the total quantum state to obtain psi 1 and psi 2 only. So this is the way that one can actually engineer. This is the new way of thinking of quantum superpositions, and because it is cutting the state in a desired manner, so it is called the quantum scissor. So this is a new idea which we reported, that you can have quantum information and sensing out of it in a very sophisticated way by quantum scissor operation, and laser intensity, how experiment can be done and so on. Okay. Now the point is that so far quantum sensing, there are many other examples. I'm not getting into it. We have molecules, how molecule can behave like a very good quantum sensor using vibrational rotational spectroscopy. Then ultracold atom definitely have a lot of other situations. But the point is that two different aspects which I have emphasized, like quantum computing and quantum sensor. Now, are they completely independent directions? The answer is no, because all these properties are actually entangled to each other. So I'll give you one example in my lab, that a quantum computing for quantum sensing. So I'll have quantum computing for quantum sensing. Can I have it? So that was the thing that I was interested to go ahead with such example where I can combine these two field. So what I did is that I had some algorithm, and and this algorithm was, this images were fed into the algorithm. So what happens that if you look at A and B, A, C and D, E and F vertical, G and H, they are identical. However, if you go for A, C, E, G, they're different. You can see the difference if you go rightward along the row, but if you see it vertically, they're identical. And if I zoom it like anything, still you will see that they are exactly identical. And our algorithm, quantum computing algorithm, can differentiate that. So even if the interference structures, as I said, interference structures are very tiny, and that helps us to for quantum sensing. My point is, even it is a very small change in quantum sensing region, that interference pattern, your apparatus cannot detect that but a quantum computing circuit can detect it. So that is what we have given a similarity measurement algorithm where we can differentiate the identical interference pattern and a slight change in atomic interaction. So where this atomic interaction happens inside the matter. So inside the matter, say inside the gas, there are many atoms, they're interacting. So inside it is changing. Outside you do not know whether they have changed or how much they have changed. But then using quantum circuit, when you have this interference pattern, when you analyze, you are able to identify atomic interaction in a very high precision level. Okay, so which is the highest precision achievable so far about atomic interaction, which is a non-trivial quantity for many body system. Okay, so this is the example I wanted to point out where I actually able to join both the fields, quantum computing and quantum sensing. So there are more directions, molecular sensing, as I said, and then Rabi coupling, optical lattices, then negative absolute temperature, which we have worked on extensively, then twisted graphene in quantum model of twisted graphene simulation, then logic gate, ultra cold atom logic gate. We are in quantum machine. We are also proposing neutral atom qubits, and government is looking for 100 200 qubits in different systems. So we have been targeting that. We also kind of tried to report to quantum machine about the sensing, different aspects of sensing we have reported. Yeah, so these are the things I wanted to point out. So I'll take questions. These are my PhD students and collaborators, mostly here, Rekwang Lee, yeah, so Lucas Salas and David Vitali. These are and Professor Panigri in one case. So these are the collaborators in my case. Yeah, thank you. Thank you so much. So I can take questions now. Yeah.
Participants are now requested to ask
Yeah.
questions.
Yeah. Because I've lost few minutes, so I've just crossed 6:30.
Yes.
Yeah.
So your students that you showed, they are all from IIT Patna or some other place?
Yeah, my group actually, my
Your
students.
group, I see.
Yeah, yeah, yeah.
I've met several of them, I think.
Yeah. You met several of them. When you
Yeah.
came, I think, yeah, I think most of them were here. Yeah.
That's
They
right.
are still here. Yeah.
I see.
One of them has just finished, he has just left.
But does your work require heavy computing? I mean, it's traditional computer. I know
Uh,
it's quantum computing, but does it involve using a lot of computer work? I mean,
No, actually, I like to work on analytical things. Most of the things, practical system, but calculations, and yeah, most of them are based on calculations, experimental designing, and parameter modeling.
I see.
So
Okay.
yeah, not huge computation, but some
Hmm.
little bit of computation is required.
I see. Mhm. Very good. Anyway, anybody else, I mean, wants to make a comment or uh,
In
I
chat,
have some.
so,
You can look up the chat.
yeah, I'm looking at it.
I don't know if I'm also trying to see.
Uh,
They are all saying hello, hello, I think, Someone
Yeah.
has sent a lot of links or something. What is that? You
No,
have
I
sent,
sent the link. I sent the
what
link.
is that for?
The YouTube link for that we had all this quantum test session, all the 5 days of it.
Vikramganj, yeah.
I see.
Okay, ठीक है.
Will there be also in the YouTube later on, Himanshu?
Yeah,
Yes.
it's there on the YouTube actually.
It will remain there, right? Okay.
There is a YouTube. And I have a question. Since
Yes.
people don't have a question, I mean, I would rather have some other students asking questions. Is there any, Himanshu, can you ask them?
Uh,
From YouTube, if there is any.
yeah. Uh,
कोई है? I think someone is trying to join, but okay. You are letting them in, na? Whoever wants to join.
Yeah.
Okay, take care. Besides the harmonic oscillator, which is very close to a, how should I say, to a classical state, as you said, are
Right.
there other quantum states which are almost classical?
Uh, no, actually, mostly we look for this particular state which is not decaying is for harmonic oscillator.
Yeah.
But for other system, we look for coherent states like different ladder operators can work there, raising, lowering operators with different symmetry algebras. For example, a molecular system, if we talk about vibrational levels, so then AC2 is the group which is the symmetric group. Now we have to find out ladder operators for AC2 group and then corresponding coherent state for that. And that wave packet will be the most classical for that system. So,
Okay.
but those wave packets will definitely decay because harmonic oscillator is such a gifted system that this is the only system where wave packet does not decay. Yeah. And Schrodinger had that level of intuition to predict it in 1926.
I see. It also has the minimum uncertainty.
Minimum
Delta x,
answer.
delta px is h cross by 2.
Yes.
So, unlike,
Yes.
say, students can just verify it, unlike particle in a box or something,
Right.
which have
Right.
much larger uncertainties. Yeah.
Right.
Okay.
Harmonic oscillator advantage is that this is Gaussian, so student can have integration
Mm-hmm.
and
Oh,
they will be able to find the uncertainty also.
yeah.
Yeah.
That's true. I mean, it's exactly integrable then.
Yes. Yes.
Yes, you can integrate the thing.
Yes.
Yes. Okay. Okay. All right.
I don't see anything.
Find
If
one
anybody is,
question.
they can definitely contact me for.
One question I found on YouTube
Yeah.
pertaining to qubit quality. That how we ensure high fidelity qubits with lower error rate.
Uh, I could not hear properly, Manshuji, because it was echoing. Can you repeat once again?
तो ये दोनों चल रहा है.
Mm-hmm. No, just repeat the question.
The question
Even I
is,
didn't hear it. I couldn't hear it.
how does high fidelity qubits with lower error rates is essential for performing accurate quantum computations?
High fidelity qubit. Yeah. So that's very important. I do not have that pictures, because I did not want to go into that level. That when we somebody design a qubit in a physical system, so several things are important. First thing is that it should be 0, 1. That means they should be orthogonal, completely orthogonal measurable quantities. The second thing is that in experiment there should be the fidelity should be very high. So if I measure 1, it should be completely 1, and 0, they are completely orthogonal. So that's definitely very important. And also, defining 0, 1 may not be enough. So when we have bit logic gate operations, there also this fidelity matters a lot. So to have a good performance qubit, one has to definitely check, fidelity measurements before going to any other algorithm, testing algorithm and all. Yeah, that's important.
Okay, got it. Okay. So we I will share your mail ID. There's one
Yeah.
question with scalability also.
Yeah,
We-
scalability also one has to optimize things like I cannot use circuit or quantum computer. Scalability definitely an issue and depends on the system to system. Actually, it is not very definite that which system will ultimately give us a better quantum computer, but it looks like so far that superconducting computer will do that. We have been thinking that, but then progress is not that promising in the sense. So nowadays people have been thinking of hybrid computations like quantum classical hybrid. So IBM recently has taken up vision of say 5 to 8, 5 to 7 years of 10 to the power 5 qubits using hybrid computation. So there, superconducting qubit is the main base. However, people are also working, for neutral atom qubit and then optical qubits where quantum continuous variable computation is in place. So many other approaches, yeah, cold atom approaches, ultra cold atom approaches. NMR is also there. And there are new neuromorphic computing and IV center, there are a lot of approaches are there.
So, thank you so much, sir.
Yeah.
Very nice session. So now I'll request Dept sir to kindly start the session. Are you ready, sir? You are muted.
Yeah, but how much time do I get? That's-
Up to
No, because
20
otherwise,
minutes. If you could take 20 minutes.
no,
Up के ऊपर.
otherwise it would be better to have a separate talk
Okay.
sometime. Because I was
So,
planning on the mathematical aspects of these postulates of quantum mechanics. So it will take some time.
okay.
So it will be
So-
better if I
Schedule it separately.
reschedule it some other time.
Okay. Okay. So, I think we can conclude this session today now. It was a very effort. All the resource persons have contributed collectively well. So on behalf of IPTRC 19 Bihar, I thank to each one of you. Vijay sir, Anden sir, Utpal sir, all the resource persons. I'll request if somebody could say, place a final feedback over there.
Any participant would like to say something? I mean, these talks will be on the YouTube, and I was actually looking forward to Amrendraji's talk, but it is good that he will give it separately so that we can listen to him at leisure. I would also, from behalf of all the audience, I mean, because all we are, I was like to thank you, Himanshu, and Amrendraji, and RC19. Thank you, of course, to Utpal today, but basically, you have pulled through and organized a very good program, which at least will kickstart this interest in quantum computing and quantum information and sensing in Bihar. And maybe it will be more broad-based than being just confined to one college or two colleges in Bihar. Thank you.
Thank you, sir. Any more feedback? Okay.
Okay.
I'll request RC President and then Narayan sir.
So thank you all of you, the listeners as well as the resource persons, and I hope we'll soon meet again with some new programs. Thank you.
Yeah, we have to continue. One more thing I wish to share with the participants here, that we have also planned to conduct the offline session, which is going to start from the 21st of this month, 21st, 27th. The offline program, which is going to be held in many of the university headquarters, college centers, schools as well. And we are looking forward because there are many school principals, college teachers also, if you want to say conduct such session in your institution, we are ready to shoulder the responsibility with the resource persons. So it will be a nice effort. So I think we should conclude now.
Yes.
Utpal sir, can we have one session at
Yeah.
IIT Patna?
Sorry?
One session at IIT Patna.
Yeah, definitely. आप अरेंज कीजिए, अब हो सकता है यहाँ पे एक दिन फिक्स करके. हाँ.
Yeah.
Yeah, sure. फोन पे बात कर लेते हैं हम लोग.
Okay.
Sure. Yeah.
So thank you so much. Now it is the time we
Thank you
conclude.
so much. I
Thank you.
enjoyed it. Yeah. Thank you.
Okay.
Yeah.
Lifetimes.